Well, hello and welcome to another DevNation. We are going to have a lot of fun today, and I'm super excited to be with all of you guys because we have a very special guest star today. We have Tristan. Tristan is our expert on in-memory data grid technology, in-memory data caching, so we're going to have a lot of fun talking with him about this topic, which is Redis versus Infinispan. He is our resident expert at Red Hat, and he's going to give us a great presentation, I'm sure. Tristan, please go ahead and introduce yourself and let people know who you are. And then, of course, if you have questions, by the way, throw them into the chat, and I'll be getting them from there and relaying them to Tristan at the right time. Tristan, over to you.
Thank you, Burr. Hello, everybody. My name is Tristan Tarrant, and I'm the lead engineer for Infinispan here at Red Hat. And I'm also a principal architect for DataGrid, which is the product on which Infinispan, built on top of Infinispan. Obviously, when comparing Redis to Infinispan, this is going to be a little bit biased, but I'll try and be fair, Burr. So let's see how this goes. Okay, I'll start sharing my screen. I have a part of this is going to be a presentation, and a part of it is going to be some coding. So I hope to be able to get the message across loud and clear. Okay, so Redis, keep things in memory. What kind of things, and why would you do that? Obviously, the answer to why is obvious, because it's fast. Memory is probably the fastest to store your data in. And what do you do it? What can you use it for? So obviously, caching is the primary use case. So you have data coming in from your database, your web services, wherever, and you just read it from there and put it in the cache so you can look it up much faster. And you can also pre-calculate some data. You're collecting data coming from all these sources, and you're doing something with it, and you want to the digested item in some place so that you can reuse it without having to calculate it again. Another useful use case is sharing. So especially for data that changes quickly, changes a lot. One very useful use case is in sessions, use web sessions. So think of your shopping cart. You store the session inside in memory, and you can share it across your front end. So in case one of your front ends fails, even geographically across to another site, you still have your session and you haven't lost your customer. But obviously, these stores are a bit more advanced than just plain dumb sharing, but plain dumb storing of data. And you can do interesting things with them. And they have some features which make them closer to what a database does. And we'll see some of these things in this. So let's see what containers look like. So Redis is a key value store. Obviously, everybody knows about Redis. Keys are strings, values strings as well. But actually, you can use any kind of byte array in both. They're safe strings. So you can use any kind of binary data in there. But strings obviously are the most convenient form of data. Values can behave as numbers or as bit sets. So you can use them as counters, or you can pack Boolean values in there really tightly. And Redis also has these very convenient composite types like lists, sets, hashes. So you can store more than one value inside value. Redis also has a cool feature, which is a publish-subscribe notifications that many applications use a lot to broadcast messages between each other in a distributed system. And data can be namespaced separate databases. What Redis calls a database is identified by a number. And these databases are defined as startup. They all share the same configuration in the instance and are persisted in the same file. Infinispan is also a key value store, and keys and values are byte arrays. However, you can add an extra twist on them and make them understood by Infinispan by telling them, providing a protobuf schema. I don't know if you know what protobuf is. It's a format for defining binary payloads in a very compact way, and it has a schema that work across multiple languages and provides generators for every language out there. So once Infinispan has this protobuf schema, it can do interesting things with that data. We also have counters, locks, and multimaps. We don't have PubSub. Always a believer in the right tool for the pub, so I'd leave that good topics based publish subscribe to things like messaging systems, which can do that job in a much better and more reliable way. But we do have listeners, so you can register a listener on an entry or a cache on a certain type of events, and all subscribers to those listeners will receive those events and connect accordingly. In Infinispan, data is stored in named caches. Think of these as a database table in a relational database. Each one has its own configuration. You can define the type, prediction, expiration, persistence, transactions, indexing, and security, and so on. And each one is its own thing. It doesn't interfere with the others. So you can mix and match these features in your caches. And caches can be created at runtime. So you can start with an empty Infinispan cluster, define your cache. So the first of the two main topics I'm going to look at is an architectural view of Redis and Infinispan and how they handle scalability, which is particularly important because how these systems do scale, both vertically and horizontally, affects how you design your application. So Redis is a single-threaded system. So there's a thread that handles I/O, and there are other threads there that do other auxiliary operations, such as but essentially throughput is limited to that of a single core of your CPU. In order to increase the load that your system can handle, you need to create replicas of your Redis. Redis has a master-slave configuration. The data is copied from the master to the slaves asynchronously, which means that it doesn't wait. Your operation don't wait for the replicas to happen. However, you can use a command called wait that will wait until a certain number of replicas have happened to increase reliability. So the writes only go to the master. Reads can go anywhere, obviously, but if you, because of the asynchronous nature of the system, if you're reading from a slave, your read may be stale. How does Infinispan scale? So Infinispan is a very different beast. It's multi-threaded, built on non-blocking architecture. So it will automatically take advantage of how many cores. So it sizes its thread pools according to the number. So in order to increase the load that you can handle, you just add more cores or you add more nodes, and we'll see how that works. The architecture of Infinispan is peer-to-peer. There are no masters or slaves. Everything is symmetrical, and the nodes discover each other automatically. You can have both synchronous and asynchronous replication, depending on guarantees and the latency that you want from your application. And it automatically rebalances data. So as you add and remove nodes, the data is rebalanced to make sure it maintains the same guarantees that you've asked of Infinispan. So let's see what Redis looks like when you're scaling vertically, so to increase the throughput it can deliver. So you have your master node and your read-write clients reading and writing to it. And this is your data. And you can create a number of replicas, a number of slaves, and they will receive the data asynchronously. If your master fails in a configuration, you can't write more. You can, however, enable something called Sentinel, which is a system where one of the slave nodes will be elected to act as a new master. So here are the copies of the data, and you can have clients that only need to read data can access these. So you can have the writers, the writes happening on the master, and all your reads happening. Obviously, because of the asynchronous nature, you have to be careful of this difference in latency architecture between the two systems. So if your writes rely on reads, then obviously this architecture has an impact on how you design your application. Let's look at how Infinispan can increase throughput. I'm looking at what Infinispan calls a replicate cache. So every node has this identical copy of actually every cache, every instance of that cache on the nodes has that data. So I have one node, and my clients are reading and writing from that. So suppose I write an item. I add a new node, and the two talk to each other. My clients can read and write to that as well. The new node has received a backup copy of the data because, as I said, every node has all the data. And if I write some more data, the data is possibly written to this new node because the owner of each key is determined by its consistent hash. So, and now node 1 becomes the backup for the entry, whereas node 2 is the backup for the blue entry. And as you add more nodes, the data is automatically synchronized between all the nodes and kept in sync. And they all talk to each other, so they don't go through a master or anything. So replication happens, communication happens between all the nodes. So here I add the green item, and the green item is owned by node 3, and all the other nodes get a copy of that. So every key has a primary owner, and that's where the writes go. But all the other nodes in the replicated cache are backups of that. So as you can see already, I can handle much more throughput in writes as well as reads here compared to Redis. And also, if one of my nodes fell down because of its completely symmetrical nature, the system heals itself. And you can add more nodes to increase capacity. Now let's look at how Redis handles horizontal scalability. Does this by sharding. So Redis has a concept of slots. So you need to assign slots to your masters, and the data will be spread across these. So your writes are happening now across multiple nodes. So now you have 3 masters who can read and write. And it's a bit similar to the primary owner that I showed in Infinispan in the previous slide. And obviously each master can have a slave or more slaves, and each one receiving copies from the master they're connected. And same as before, you have your read-only clients reading data from those slaves. The problem here is that if each master only knows about the data that it owns, can't talk to the other masters and the slaves as well, obviously. They only know the data from the slots they own, and they can't collect data, read data from the other nodes, so they're not aware of that. So if you want to iterate data, you need to go through all your nodes. Let's look at how Infinispan handles horizontal scalability. So here we have our initial node and clients writing to it. I add a second node and it gets a backup, same as before. And here I've configured 2 owners for the data. I want 2 copies, which is identical to the Redis cluster I showed the slide. So as I add 2 more nodes, the difference here between replicated mode we showed earlier is that these 2 nodes are not getting copies of the blue and the red, but they store the green, for example. So you see I've increased capacity. So the total capacity of the system is the sum of all the memory divided by the number of owners I have. And again, same rules apply that I described for replicated case. So in case one node goes down, the whole system rebalances itself. So there's always a primary owner for the data. It heals itself and nothing changes. Clients are not automatically informed of the change and automatically know where to find primary owner and where to send their writes. Even if clients don't connect to the write server to do the writes, the server can hop over to the primary owner to the operation. So you can see the clients don't need to be aware of how the Infinispan cluster looks like. Reads and writes are the same. In Redis instead, you need to build your application thinking about who is a writer, which I think puts a little bit extra burden in how you design your application. After looking at an architectural aspects, there are many more aspects that I could look into, but that's the one I want to highlight. And now we'll look at a developer aspect that's part of the user experience of using Redis. So key value stores are obviously very simple. They allow you to look up things by keys. But obviously now key value stores are a bit more clever and can do things like secondary indexes. So you can fetch data, find data by looking at other elements inside your values. So a quick look at how Redis implements queries. So it's more of a DIY approach. It uses sorted set index, and you have to maintain that yourself. So every time you write a value, you must update index, and every time you change a value, you must update that in. So, and now I'll switch over to my ID, and I'll show you a simple example of how you would search for an entity. Here I have a sheep taken from the sheep, and my sheep have name, gender, and age. And I want to store many of these objects in my eValue store, and I want to find them by their age. So this is a simple, in theory, it's a simple POJO. There are some annotations in here that I ask you to ignore for now. You should focus on just the fact that we have these fields, getters and setters, usual stuff. And let's look at our Redis application. I'm using, Redis has plenty of clients for plenty of languages. Here I'm using the Lettuce client, which very nice. But there are many others like Redis and so on that you can use for Java. Here I'm connecting to my Redis cluster. I have a Redis cluster with one master and one slave, and I've set the read that can happen from any of the nodes. Doesn't matter. Okay, so here I have I construct my objects. I assign an ID, a name, a gender, and an age to my sheep. And the important thing with Redis is how you're storing that data. So I'm going to use a hash map. So each of the fields in my objects are going to be stored as named hashes inside my entry. So I create a key, which is a combination of a user colon and the ID of my object. And inside that key, I store my map. Now, I need to store the age to a sorted set so that I can then look that up using what Redis calls a range query. Okay, so let's do that now. So I use the zadd command in Redis. And I need to store this index in a key. So I'll call it user age. Okay, and the first thing I need to add is the age of my sheep. This is the value I want to search for. And then the actual key that maps to that age. Okay, so I'm now adding to the sorted set the age of the sheep and the ID that will allow me to retrieve it. So as you can see, if I make changes to my object, if I replace the key, delete it or something, I also need to manually update my index. So now let's query this cache to find all the sheep that are between a certain age. So I use Redis range by score. E is obviously user age, which is where I've stored my index. And then I create a range, and I have an upper and lower value. So I want all the sheep that are between 4 and 7. And what is that going to return? It's going to return the list of keys that match that range. And then if I want to retrieve actual objects themselves, I need to then perform a get for all of those. So let's do that. I stream the list of keys that are being returned. I map that's being returned. So I'll go one line there. I've got my key, and now I perform an an hgetall on that key, which is going to return all the fields in the hash map where I've stored my sheep. And then which one of these I printed out. Okay, so as you can see, this is quite nice. It allows you to, I like the fact that it's using another entry in your, another key value to store this index. However, you need to plan ahead with the type of queries that you want to do. So if we now want to do a query by gender, I also need to get the second index for gender. And don't get me started on how you would combine those queries to add multiple predicates. So searching both for gender by name match and by age at the same time, you would have to add multiple index or use other features, and you have to maintain manually all those indexes when you add, remove, modify your entries. So there's a lot of burden put on the developer into thinking and planning about these things. Infinispan, how does Infinispan do that? I mentioned the fact that in Infinispan you can define you can tell the cache that it's storing a certain type of data, and you define that data with a protobuf file. So a convenient way, I'm going to show you one way that I've done this here, which uses annotations, but you can also do it manually by providing your own protobuf file. There are some annotations that we provide that automatically map this entity into a protobuf file. And let me find it here. It should live under here. And this is the protobuf file that was generated for that entity. As you can see, it has some magic comments in here, and this is our way to tell Infinispan, because protobuf obviously is a well-defined standard and we can't extend it with our own thing, so we've added comments in here, like docklets that tell it how to index the data. But this is all automatically and for you, and you can it if you don't want to. So I'm now stored my sheep here. Here I am loading that protobuf file into my schema protobuf metadata cache. It's a cache like any other. So, whoops, code here, and I'm putting the sheep protobuf file, reading it from the file. And then I'm creating a query cache using a certain configuration at runtime that's going to store my data. Let's see what the query cache definition looks like. Here I'm using XML. I could also use JSON. So it just says that it has indexing enabled. Okay, let's go back to our query class. And I've stored my entries, and that's all I have to do. I just add those entries, and because of the fact that I've told it to index those fields, it's going to automatically index them for me and keep indexes updated according to the changes I make. Okay, so I have my my query factory here, and I can create a query. And in Infinispan, a query is in a query language called ICL, which stands for Infinispan Query Language, which is a subset of, it might look a bit like JPQL, but it also has full text extensions. Our backend is Bean for indexes, and therefore we can do all sorts of neat things with full text searches. Okay, so I'm just going to do the same query that I had before. So my query from DevNation sheep, S, where s.age is greater than 4, and s.age is less or equal than 7. And this is actually going to return those entries directly. It's not going to return a list of keys. So I can actually, I don't need to fetch them again. So I don't have to do a second round trip to the cache to fetch them. They're returned all in one go. So for each, and I can print out those entries. Nice thing about this language, this looks a bit like SQL. So obviously we can combine it, do all sorts of other fun things. For example, we can say, I want to find where all the sheep that are above 4 years old and and whose name starts with the letter S. So very flexible. I just make sure that I have indexed the fields that I need, and I can then perform any kind of queries that I can come up with later. So I don't have time. Okay, so I want to describe a few of the features of Infinispan Query. So you can do indexed and non-indexed execution, so you don't have to index everything. Obviously, with non-indexed fields, execution will be slower. You can filter on various properties. You can have embedded objects. You can have collections inside your object, not just limited to a flat map of keys and values. And you can do projections, aggregations, sort, and all sorts of complex Boolean expressions. And obviously, as I said, all the full text goodness that comes from the scene, which is obviously. So, I want to talk about other things like transactions and security, which are features that where I feel that Infinispan has the edge over Redis. But I see that we've reached we're near the end, so I'll come up with a list of conclusions. That Redis is actually very good tool. It has a tiny footprint. It has tons of clients. You can find it everywhere. It has integrations with everything. It's very, very popular. And it's very popular because it's very easy to use. And that's the biggest strength it has. However, it has a number of shortcomings. It's hard to scale, both vertically and horizontally. The way it clusters affects how you design your applications. You have the split between where you can write to or where you can read from. And it has a cumbersome API, which you have to combine in creative ways. And you have to think about that API when designing your application instead of just thinking, I'm storing stuff there. I want it to be efficient, and I want to be efficient in how I develop my code. Security, I feel, is an area where Redis has very, very basic features. Redis 6, which came out last week, has improved this greatly, although it's still not on par with Infinispan. So Infinispan is the good things are that it's easily scalable, both horizontally and vertically, and it has an API and an architecture that don't get in the way of the application design. Well, not as much as the annotations add to your entities. On the other side, however, obviously there are a few clients. There's a Java client, there's a C++, C#, Node.js clients. However, Infinispan can be accessed through a high-performance hot rod protocol as well as through HTTP, and you can obtain your JSON objects transparently, your protobuf objects transparently translated into JSON. So interoperability is very strong there. So even if there's not a client for your language, it's easy to whip one up using it. And obviously, being written in Java, it has a larger footprint, but that makes it scale a bit better. For extremely large heaps, for example, we've tested Infinispan with over 1 terabyte heap. We have an off memory management. And Quarkus, you may have heard of that, has allowed us to build a native version of Infinispan that makes it much, much smaller and faster to start, faster to scale, and with a leaner footprint. So that's coming soon. We'll be blogging about that very soon. So, Burr, I think I've talked about some of the things I wanted to highlight. Infinispan comes out as the clear winner here.
What's awesome is we actually had a great conversation in the chat. The nice thing is William Burns, Wolf Fink, you probably know those names. Thank you, by the way, Wolf and William, to be with us today, because we actually had a great conversation about the various ways the topology might change and who owns what, and where's the hash come from, who gets the right, and load balancers. It was really a great conversation, which you missed on. We also enjoyed your presentation too, by the way. That was absolutely fantastic.
Well, thank you.
I got one key question for you, because I think we answered the technical questions all along the way, but one big question. If Infinispan is so much more awesome, because you proved it in this presentation, right? It is so much more awesome. Why is Redis more popular?
Yes, I think it's because it's easy. It's and smaller. I think those are the two things that have made it very popular. It's easy to get into. The key value functionality is top notch. All the other features, as soon as you get into more advanced features, then I think it starts showing a bit of the limitations. But obviously, for most simple applications, I think it's a great fit. And I wouldn't use Infinispan in those cases where you just need a very simple, unreliable single node cache.
Yeah, I think that's what it is. If most people just start with a single node, I just need a cache, and that's all I want, and therefore Redis just kind of point and click. You can solve that problem. But once you get into the distributed nodes, the transactions, the distributed querying capability, the rebalancing, right? You basically talked about vertical scale, horizontal scale. Yeah, then Infinispan really is a better solution.
Indeed, it is.
We are out of time, and I have to switch gears. We are starting a new stream in about 27 minutes. So, but for the people here on the line right now, there was a good question on, hey, where's my Python client? Someone says, DJ Maddie wants to know where his Python client is. You got one for him?
We are writing one, yes. So, and if he wants to contribute, he's very welcome. There's a Python client in the works.
Okay. And then does it work with embedded mode on Quarkus? I know you can do embedded on a regular JVM app, but how about embedded on Quarkus native?
Right. So there is, and actually our server version of Infinispan is obviously built around, and we can build that with Quarkus. We're building that with Quarkus into a native applications. So the extension is there. The question should be asked to the Quarkus guys about how we're going to handle that. Hopefully, we'll see how to implement that. We do think that for most applications, you want to externalize that to a separate data grid so you can make your scalability independent, because pulling in a clustered component in the application brings all sorts of complications, especially if you're running it on Cube. And then you need to think about discovery, scaling without losing data. So do you really want to bring that complexity into your application, or do you want to delegate it to a server that does that already for you?
Especially in a dynamically scalable environment like a bunch of pods running in OpenShift and Kubernetes.
Exactly.
The last question is, hey, where's my operator for Kubernetes and OpenShift?
It's there. Infinispan, it's on GitHub. Infinispan operator. It's there.
Yeah, I know. So if someone on the chat can put a link to it, I knew it was there. I just don't know where it is myself. Galder's been working on it, right? But I don't know where it's gone.
Yes.
Okay. Well, thank you so much for your time today, Tristan. I really enjoyed this presentation. I'm so glad you assembled.
Thank you for having me here.
Yeah, it answered some great questions for us. The chat was fantastic. I thank all our listeners. But we do have to shut this stream down to start our next stream. We actually have an OpenShift-specific session. To this point, I thank you all and bid you adieu, and we'll see you in just a few more moments. Thank you, Tristan.
Thank you. Bye-bye.